All right, lovely. Thank you. Okay, so I wanted to tell you about some work that my collaborators and I have been doing and some stuff we've been thinking about to think about small-scale cosmology in the era of large sky surveys. And so my introduction's already been given. It's worth just reminding ourselves that the properties of faint and especially ultra-faint dwarf galaxies are particularly sensitive probes in the number of them, in the velocity scales of them, and indeed in the structures, right? So we've seen this plot also of the magnitude versus the half-light radius with the Milky Way and M31's galaxies here, and it's incredibly sensitive to model physics. And so the properties of dark matter halos and the number of dark matter halos and how galaxy formation physics works is illuminated by these incredibly tiny galaxies. The problem is that we only really have a good census of these around the Milky Way and to a certain extent Andromeda, and that we know that this is a dangerous problem. So we have good evidence that many of the ultra-faint satellites of the Milky Way fell in along with the LMC. And inasmuch as every galaxy has its own special merger history, bringing in its own little set of satellites, we realize that generalizing our model constraints based on a couple of systems with particular merger histories is going to be dangerous. And indeed, it should influence the number of satellite galaxies. So this is work that Richard D'Souza and I did a couple years back with the Elvis simulations, which are dark matter only, but this has been done with hydro models too. It should affect the star formation histories of these dwarf galaxies. And so here we have like the star formation shutoff time of Milky Way and Andromeda satellites, and they're completely different. And they're completely different because the satellites were delivered at particular times. It's when the ram pressure stripped the gas from these star-forming dwarf galaxies and shut off the star formation. The Milky Way had the LMC merge with it a couple billion years ago. M31 had delivery of satellites 6 billion years ago. And these have consequences in dynamics, but also consequences in terms of spatial distribution. Andromeda satellites are mostly on our side of Andromeda. Right? This was discovered a couple years back. And so they're not phase mixed yet. Right? So there's tremendous amount of richness in these dwarf galaxy distributions and their properties. And we can't generalize from just two cases to try and constrain our models. And so this has motivated searches that we've heard about and that we're going to hear more about around nearby galaxies to try and find their satellites. Integrated light has made great strides in this. And so with resolved like HST follow-up, like you saw, or semi-resolved, think surface brightness fluctuation follow-up. So this is an example from the ELV survey. You find these low surface brightness blobs. You see which ones semi-resolve into stars, and then you can use those to understand the bright dwarf galaxy content. And we've learned a hell of a lot from this approach. And so this is a plot of the number of classical satellites, brighter than -9 in absolute magnitude, against the stellar mass of the central host galaxy. And it scales. There's scatter. Some of that scatter is expected in the hydro models, but some of that scatter correlates observationally with other properties to do with the merger history of the group. And so this is actually two plot from Bersin's paper that I hope we hear about tomorrow. And so there's a relationship between number of satellite galaxies and the mass of the largest merger ever experienced by the host. And there's a correlation between the number of satellites and the local environment, right? And so there's extra information. The number of satellites is being affected by the properties of the hosts. And we know that ultrafaints are particularly sensitive to model physics. And so this motivates a search for ultrafaint dwarfs around other galaxies. We've just heard that you cannot do this with integrated light. These are see-through galaxies. You have to resolve them into individual stars. I illustrate this using we have a Subaru data set that's about LSST 10-year stack depth. And so this is what the sky is going to look like, or a little tiny patch the sky is going to look like with LSST data. with 10-year stack depth. It's filled with galaxies, or yeah, background galaxies. I'm going to add an ultrafaint to it at M81 distance, right? So I did that. You might not have noticed anything happen. It's kind of depressing, honestly. So there's this wee thing right in the middle. If you can, thankfully, I put down a circle. God doesn't circle these things, and so that's what makes it hard. But you see that there's a few stars that appear, very faint. They kind of look like background galaxies, and this is a negative 600 parsec half-light radius ultrafaint. So our and other groups have been trying to find these things using that kind of resolved star technique. Um, and so you'll hear more about this work. It's happening in a few nearby galaxy groups. We happen to adopt M81 along with the Okamoto group. And we've been using Subaru data for this. And so it's basically 10-year stack depth with great seeing. And so it really is a template for what success should look like in the Rubin era. I want to emphasize what previous speakers said about how painful star-galaxy separation is. We have quite a bit of HST data in these fields. And so this is real HST stars that we have here, and we show just which fraction of them were covered with anything in this Subaru data. And so most things are recovered, but there's a lot of galaxies per star, right? And so this is the plot of the number of contaminants per recovered star. And so there's 10 to 15 or so faint galaxies per recovered star. So we're completely overwhelmed by galaxies. So it's like, well, you know, maybe we'll just use little things. And so that's what you do with this yellow line. Or you can, and so you still end up, it's doing better. You get rid of some stars, but you have some contaminating galaxies. You can decide, well, I'm going to select my color too. And so I get rid of some more stars. This is really depressing, by the way. But you do get rid of a lot of contaminants. And then you can say, well, you know, folks do machine learning, so you can try supervised nearest neighbor or other approaches, and you can get a little bit more, some of your stars back and minimize the contamination a little bit more, but you still end up, for every star you have, that there's one or more background galaxies. It's really kind of disappointing. All right, so we do the same job that we just saw described. You have maps of metal poor stars. You look for wee overdensities. You have to look for really, really significant overdensities because you're running a trial on lots and lots of positions in the sky. So you actually do need to have a pretty high bar, and then you still end up getting it wrong. And so this is the map of blue RGB star density in the M81 group, and you can see all sorts of weird, you know, artifacts where the pipeline just decided to crap out in dense regions, and then you'll see the influence of bright stars and things like that. Right? So real data is actually kind of messy. So in addition to recovering all the known M81 dwarfs, we found a bunch of candidates. And so the candidates are all kind of circled in red, and the known ones are circled in yellow. We felt pretty smug about one of them. And so this is this guy here. That's a picture of it from Subaru, and it's a Tucana B analog, right? And so it's relatively high surface brightness. You can just see it. We also recovered a bunch of low surface brightness dwarves that really do look like nothing, and they should look like nothing. That's what you'd expect for a low surface brightness ultra faint galaxy. We pointed HST at some of these as part of a larger program. We have a snapshot program to look at candidates in nearby galaxy groups. And we ended up confirming 4 ultra faint dwarves, but we also ended up ruling out all of the low surface brightness ones. And so this is, we didn't check this guy, but we managed to rule out these ones. We confirmed these 4. And these end up being, well, okay, so I wanted to, before I go to getting excited about the ultra faints, I want to underline, and Will did a great job of this earlier on, so I want to add one to his kind of list of things that can go wrong while doing this, right? So background galaxy groups are expected. You can go to blank fields and do the same thing, and you end up you can somewhat characterize how frequently they should be, and indeed you find that they contaminate these samples. Um, One thing we didn't anticipate is that MED1 group has, thank you, has blue helium burning stars that have Subaru colors that put them on the RGB. And that ended up actually creating overdensities that are overdensities of stars. They're just not dwarf galaxies. And then finally, edge effects, and that's my bad. I'm not I didn't have awesome ways of dealing with the edges of, for example, bright star exclusion regions, etc. And that can end up boosting the significance of something. And Will showed an example of that earlier too. Sergey smiles because I think that's a story, a part of his life too. So we ended up confirming 4 of these. And these MED1 ultrafaints are diverse, right? So these are RGB colored stars, and these from HST. You have very compact ones going to incredibly diffuse ones, right? There's an order of magnitude range in half-light radius. And some of these, so for those who don't know, ultra faint dwarfs usually have an exponential light profile. And most of these do. One of them has an incredibly concentrated profile. It's fit best by a Sursich index with n equals 4, right? That's really very unusual. It's this guy here. It has too many stars in the middle and wings that are really extended, and you cannot fit it with an exponential. All the information criteria say, hey, this is a Sursich index, not an exponential. Another one of these is incredibly elongated. It's like Hercules around the Milky Way, and none of them are tidally limited. This is probably not tides that's causing this. We do have examples of some of these types of systems around the Milky Way, but generally much fainter, right? So Tucana 2, not Tucana B, has an envelope of stars at very large radius. And our system in some senses looks a lot like this, but it's 4 magnitudes or a factor of 15 brighter. We don't know why this is. There's some really interesting suggestions from the simulators suggesting that this could be a sign of ultra-faint dwarf merging, right? The idea is that basically the envelope or the elongation are the stellar halo of these ultra-faints. It's the debris from the secondary, either lined up in a line or in a big diffuse envelope. And so it's interesting that this might be more common in the MED1 group than we see around the Milky Way. All right. So to summarize, these faint and ultra-faint galaxies, they're our premier constraint on small-scale cosmology, but we can't just rely on the local group to do this. Generalizing from it is dangerous. We have to discover these things using resolved stars, but I hope I've given you a sense of how bloody difficult it is. It's really going to be very, very challenging, even with Rubin. HST follow-up of some of these candidates shows that there's a lot of diversity in them, and more diversity than we see around the Milky Way. And I didn't super duper dwell on it, but Roman is going to help a lot too, right? But only if we decide to point Roman at a particular spot, right? Roman is only doing a 20th of the sky. And so if we want to do this kind of near field cosmology, we're actually going to have to, as a community, decide to point and map around nearby galaxy groups. Thanks for your time, and I'm happy to take any questions.